Hello out there. Purpose of today's video is to talk about solving trigonometric equations using sine and cosine and other trig graphs. Now, the basis, or rather before I get started on the examples of solving equations and using the graphs to do so, needs to be understood for the viewers out there that there's some base level knowledge about the nature of the sine wave and the cosine wave by proxy, along with the rotation around the unit circle. So it's presumed that the listener knows some of the basic non-calculator trigonometric ratios based on certain rotations. For example, rotation of pi over 6 is this far, and this represents 1/6 of the distance to pi. And then when I do that, the sine is half, which is halfway up the circle, and my sine wave is at a half. And you can see how the blue rotation corresponds to pi over 4, which gives me a square root of 2 over 2, or 1 over square root of 2, or 0.7. And the red rotation corresponds to a third of pi, which takes me all the way up to almost 87%. That's square root of 3 over 2. By the time I rotate to pi over 2, then you can see why the sine is equal to 1, and you can see those ratios repeat themselves in reverse order as we go back down to 0. So you'll see that when I solve various equations, sine, cosines, and tangents, that I'm using in my mind my understanding of this circle and how it relates to this particular curve and how the angles correspond to various ratios. So just to look at the basics, there's two different ways that you're oftentimes asked to solve trig equations. Sometimes you're asked to provide all of the solutions to a specific trig equation. In this case, it's looking for the zeros of sine of x. In other words, when does the sine of x equal 0? That's what we're solving. Now, if you thought about it, you recognize the periodic nature. We just keep going around and around in a circle, which means we keep revisiting 0 over and over and over again. And so when I look at the graph, I see that there's 0, 0, pi 0, 2 pi 0, 3 pi 0, and so on. So I can write this. First of all, I'd be writing, if I listed all of them, I'd be writing for the rest of my life and beyond. But in order to save me that kind of process, I'm simply going to write a general expression that will get me a generator for all possible solutions. So I start with the first x-intercept I see, and that's 0, and then the next one is pi units away, and the next one after that is pi units away. And so all I have to do is add multiples of pi. And this is how I can say that mathematically. You start with 0, and then you add k multiples of pi, where k can be any integer. Notice integers include negative numbers, so I can go back pi and get to the negative pi, negative 2 pi, and so on. So this generates all solutions to the equation sine of x equals 0. Similarly, the next piece says all of the values for which 1 equals the sine of x or sine of x equals 1. Graphically, you can see that the first time that happens is at pi over 2, and 2 pi radians or later. So basically a full cycle away, that's 2 pi away, is the next time that the sine is equal to 1. So just like I did before, I can generate all of these solutions simply by taking the first solution available, pi over 2, and I can simply add multiples of 2 pi. So you write 2k pi instead of k pi because the distance is double between these. Again, k is an integer value. So we can go forwards or backwards by 2 pi and get all of the ones of the sine. Oftentimes, you're asked to find values that are somewhere intermittent between the zeros and the minimum or maximum values. And again, if you're asked to do this work without a calculator, you'll be given one of the important ratios, either square root of 2 over 2, square root of 3 over 2, or 1/2, or 0 or 1. But for the other three that I mentioned, you have to do a little bit more careful analysis here. Here's why. If you're looking for when the sine of x is equal to negative square root of 2 over 2, you see I have a line here that's about negative 0.7 on the y-axis, and I can see that there are, in fact, in the first rotation, there are 2 places where that ratio is achieved. Once in the third quadrant when the circle is when the radius is rotating down, and then again in the fourth quadrant when the radius is rotating back up again. So I have to account for both of these, and as you can see, there's a variable distance apart. So here they're really close, and then the next time that we're equal to negative square root of 2 over 2 is way over here, and then there's another close one, and a far one, and a close one. So to be able to present all of the solutions, in this case, we have to make two statements. First, for the value of the solution when we're on our way down, and another statement for our solution on the way back up. So I'm going to write the first solution I have, and again, this is based on my knowledge of the unit circle and the important angles along the sine. When I see square root of 2 over 2, I know it's going to be a multiple of pi over 4. And because I'm in the third quadrant, I know that's going to be 5 pi over 4. That's 1 pi over 4 more than pi. The next one in the way down is 2 pi radians away. So I can just write 2k pi, where k is an integer, and that gives me all of the solutions on the way down. On the way back up again, then it's going to be 7 pi over 4. That's my fourth quadrant angle, and all values 2 pi radians away, or multiples of 2 pi radians away. So I need two statements, and both of these statements then combine to represent all of the solutions for the sine. Now, more common, especially in IB math, but in virtually any trigonometry course, you'll be asked, rather than presenting all of the solutions, you're more commonly asked to present the solutions over a specific interval. Oftentimes it'll just be from 0 to 2 pi, but if they want to test your knowledge of cyclical and periodic functions, they'll give you a broader domain over which to answer the question. So here we're talking about from negative pi to 5 pi. On my graph, negative pi is here, and 5 pi is way over here. So I'm looking for all the values within that span. I can use the same kind of angle generator. I just have to stop once I've listed all the angles within the fixed interval. So the first time that y equals 1/2 is at pi over 6, again, based on my knowledge of the circle. So here's pi over 6, and then that happens again on the way when the radius is rotating up. It happens again in the fifth quadrant, if you will. That's 2 pi radians later. So I can write pi over 6 plus 2k pi, knowing that k is integers. And then on the way back down, I reach 5 pi over 6, and all the stuff that's 2 pi radians away for that. Now again, I don't want all of them, so I'm going to actually have to look at the graph and figure out how many there are. Here's negative pi, here's 5 pi. There should be 1, 2, 3, 4 solutions, 5, 6 solutions total. So 3 times when I reach on the way up, and 3 times when I reach on the way back down. So I'm going to have pi over 6, and then 2 pi more, which I wrote as 12 pi over 6, so the denominators match. So 12 pi over 6 is the same as 2 pi, so I take the pi over 6 and add 2 pi. I also take the pi over 6 and add 4 pi. It's 24 pi over 6. Likewise, I'm going to take the 5 pi over 6, then I'm going to take 5 pi over 6 and add 12 pi over 6, and the 5 pi over 6 and add 24 pi over 6. And the rest is arithmetic. You simply add the numerators together, multiples of pi, and you will have the 3 angles for each direction. So a total of 6 possible solutions to this equation, y equals half sine of x. Looking at the same kind of question, this is over the interval from negative pi to 5 pi again, where the sine of x equals negative 1. So in this case, you don't even have to use the generator, because when you're looking at the graph, you should be able to just see 1, 2, 3 solutions, and they exist at the 3 pi over 2, and then again at 7 pi over 2, that's 4 pi over 2 more, and 4 pi over 2 less. So you can see 1, 2, 3 solutions. You can just list them right down. So at times, it's useful to use your generator, your k, pi, your multiples of pi, but depending on the simplicity of the solutions, you might just have to, or it might just be easier just to list them out right. All right, this is a very quick example because I've been talking all about sines. I wanted to show you how the cosine works, especially when we're dealing with those intermediate values between negative 1 and 1. Like, for example, negative square root of 2 over, or negative square root of 3 over 2. When we're working with the sines, we're working with an odd function. That is to say, the sine of x is equal to the opposite of the sine of negative x. The cosine is an even function, where the cosine of x is equal to the cosine of negative x. So it has that sort of y-axis symmetry. Not sort of, it has that y-axis symmetry about it. So when I'm listing my solutions there and back for sines, it's a little more tedious than for cosines. I'll show you what I mean. For when the sine to equal negative square root of 3 over 2, I need to consider the 4 pi over 3, which is the way down, and then on the way back up, I have another solution. And so I have multiples of 2 pi for the 4 pi over 3, and add multiples of 2 pi for the 5 pi over 3. Notice it did just say solve. It didn't say over an interval, so I gave the general solution, so I've listed all possible solutions to this particular equation. But this is just like an exercise I did recently in this video, but I wanted to show you because of the cosine and the nature of its symmetry, if you come up with the first two angles in the third and fourth quadrants, then because of symmetry, you'll have the same angles, only negative, producing the same cosine values. So instead of having to write two separate statements, I was just, sorry, I was thinking ahead of myself. We could definitely write two separate statements here. But another way to do this is we could notice that if we were to go 7 pi over 6, and then we would go back 12 pi over 6. That takes us right here to negative 5 pi over 6. So we have one on the way down, and then this one over here is on the way up. So in other words, there's negative 5 pi over 6, and there's positive 5 pi over 6. So from negative 5 pi over 6, I can go 2 pi away, and now I'm at 7 pi over 6. And from positive 5 pi over 6, I can go 2 pi away, and I'm at the next value up. In other words, instead of writing two statements for the cosine, I could simply write, get rid of all this stuff down here, and put a plus or minus 5 pi over 6. So you can utilize the cosine symmetry to say, look, if we have one this way to the positive and one in the negative direction, then I'll get both of the special angles that I need, and then I just have to go 2k pi away from both of those. So use the symmetry of cosine whenever you're asked to solve those. Now, this next set is a little different because instead of just saying solve, I've given a specific interval. So once again, I just wanted to demonstrate that you could use the generator or you could just list the numbers. So I'm not so sure about what 4 pi over 3 minus 2 pi is, but I can see that it exists on the graph. So I say 4 pi over 3 is the first one, and then I'm going to go 2 pi radians back, so that takes me right here. Then the next one is 5 pi over 3, and I'm going to go 2 pi radians back. That gets me here, and that'll give me all four of my solutions. So rather than using the k to generate all, I'm just writing these two, and then my only next step is to do the arithmetic here. And this gives me the four possible solutions based on the fact that we're going from negative pi to 3 pi. So looking at the graph, I can see in that fixed interval 4 possible intersections. Whereas, when working with the cosine, again, notice the symmetry. If the cosine of x equals negative square root of 3 over 2, we can just go plus or minus 5 pi over 6 and plus or minus 7 pi over 6. So, super easy to get that one also way down. So make sure you pay attention to the boundaries, though, and that you're completing, or your graph shows all the possible solutions within those boundaries so that you don't accidentally forget some. This one, real quickly, just to show you about how tangents work the same way, except that the graphs are different. For a tangent graph, we know that the tangent of 0 is 0, tangent of 45 is 1, and the tangent of pi over 2, or 90, is infinity. So when graphing a tangent that's shifted up 1, I start at 1, then at 45 degrees I go up to 2, and after 90 degrees I'm at an asymptote. Then, coming back from negative infinity, I would be at normally negative 1, but I'm just going to put that up 1 to 0. And then at 180, I'm up normally at 0, but I'm moving that up 1. And again, at 1 or 225, I will also be up to 2. So basically, you can see the whole tangent graph, all of it has been shifted up 1. But before I drew that tangent graph, you'll see I had 1, 2, asymptote, 1, 2. That's to get a full tangent cycle. So once again, I went 1, 2, asymptote, 1, 2 to get another tangent cycle. And so use those anchor points to make sure your graph is accurate. Anyway, if you are being really accurate, you might have noticed that the solutions, that is, when is tangent of x plus 1 equal to 0, you might notice that 135 and 315 make sense on the graph based on the symmetry and nature of that tangent graph. If you didn't notice, you can, of course, do your analysis. So you start by subtracting 1 from both sides, and then you can put in a unit circle and notice that here at 135, the tangent of theta is equal to -1, and again here in the fourth quadrant, the tangent is equal to -1. So that gives me the two solutions that I already saw from the graph. Now it's fully supported. Sometimes you can use identities like the sine of theta over the cosine of theta is equal to the tangent, and then we get sine of theta equals negative cosine of theta, and you can use your analysis of the unit circle to figure this out, that the sines and the cosines are opposites in the exact same places. That is to say, if we have a 45-degree reference angle here, the sine's positive and the cosine's negative, but the same value, and here the cosine's positive and the sine's negative, but the same value. So another way to find the same truth. I'm going to end this video with one last example because sometimes you might be asked to find exact solutions, but you will be allowed to use a calculator. So you have to know how to do your trigonometry without a calculator, but you can use a calculator to help you understand what it is you're looking for. And it's a pretty valuable tool, and it shouldn't be overlooked. So first of all, recognize that to get cosine squared in a graphing calculator, you need to put the entire cosine in parentheses and then square it because we don't have the cosine squared shorthand notation in the calculator. When I observe the graph, based on my window, I went all the way up to 2 pi. I can see that there are 4 solutions. But this is one part you want to be careful of. You see, it says right here that I've shifted the graph to the right pi over 3. So that's here, pi over 3 to the right. Means that the first solution I get on my unit circle is actually going to be the second solution in my graph. So I'm going to have 1, 2, 3 in the positive direction, and then another one in the negative direction. You'll see what I mean in a second here. Solving it analytically, we're simply going to do algebra, just like we normally would, to undo everything. So the first I'm going to undo the square by taking the square to both sides. You have to remember, though, that since this is a variable expression, when you take the square root of a square, you have to account for the possibility of it being negative. So we have plus or minus 1 over square root of 2. So that's what we're looking for at the end of the day. Based on my knowledge of the circle, pi over 4 and 5 pi over 4 give me, pi over 4 and 7 pi over 4 give me positive cosine ratios, and 3 pi over 4 and 5 pi over 4 give me the negative cosine ratios. So all of the pi over 4 odd multiples end up being the solution to x minus pi over 3. So I write all of those. Now you'll see what I did is I had the circle and I went 1, 2, 3, 4 in the positive direction. That would give me 1, 2, 3, and then there's another solution that's actually not in my domain, which is why I had to go backwards here. So I went pi over 4, 3 pi over 4, 5 pi over 4, and then I went back and went pi over 4 in the opposite direction to cover this little guy right here. Now, that's taking the inverse cosine of both sides to produce these 4 angles, and then all I have to do is take the inverse cosine, add the pi over 3, and the rest is just arithmetic. I'm sure you guys can handle that. But the reason for showing this again is I have exact answers. All 4 of these are exact answers. But if I were to go to a calculator and use intersection to solve this equation, I would have decimals. So it's important to be able to do the exact work even if you're using the aid of a calculator. This one I'm not going to talk about, but you can freeze frame and look at it at the end because this video is going a little long. And at the end of the day, this is an application of the same techniques that I showed you. So at least you can appreciate to some extent how you can do the work in somewhat applied math. So anyway, sorry for the long video, but thank you for watching. Have a great day.